Hey, welcome. Today I'm going to do, I think, two more examples of some KVL, KCL circuits with maybe a little bit more complexity than I've covered so far. I'm just trying to cover slightly different questions than I've already addressed, but these are really similar circuits that you can apply everything that I've already discussed in the past videos to. So let me draw an example circuit to start. Okay, here we go. I've drawn up a circuit here with, let's see, 1, 2, 3, 7 elements. We have element A, B, C, D, E, F, and G. And there's various configurations here. It might be a good exercise for you to start by asking yourself, whoa, do I see anything in series? Do I see anything in parallel? And what things are neither of the two? Are there any that are both? And that's not the specific question that I'm about to ask right now, but when you look at a circuit, a lot of times you can simplify the problem by identifying these special scenarios. So it's just a good exercise. Anyway, what I've drawn here are the voltage polarities across each element as well. And now let me pose a question. I'm going to ask just to identify the nodes in this circuit. Okay, think about that for a second. What do I mean? I talked about what a node was, I think, in several videos at this point. And all it is a place where one or more, well, two or more, let's say, and I guess you could say a single circuit element. There's a node on either end, but that's not really a circuit. So this is a circuit, and a node will be any point where two or more elements are connected by an ideal conductor. So the first thing to do, especially, this really matters when you're talking about solving problems with KCL and KVL, is in particular, let's say you're using Kirchhoff's current law to identify the currents going in or out of a node. Well, first you have to know what a node is. So maybe pause the video and think about it, and count them up. Have a guess of how many nodes you think they are and where you think they are. And then I'm about to draw them in. Okay, let's start. We'll start easy. Again, anytime you have two elements connected and in a super simple configuration in series, let's say, so I'll start with B and D. B and D are in series. And for that matter, so is G. So B, D, and G are all in series together. And anytime you have elements in series, you have that one end of one element and one end of the other element are connected together with this ideal conductor. So this is actually a node. And let me draw just a little dotted circle around that to indicate that this is a node. And this is the most trivial case, but it is true. And like we know about elements in series, they actually share the same current. So you would never actually need to do a real nodal analysis here, or a Kirchhoff's current law exercise, because you just know by virtue of the fact that they're in series that they must share the same current. But nonetheless, this is a node. And by that same token, we can circle a little node right here as well. So D and G also make a node. And you know what? Another reason it's useful to talk about nodes in circuits is even these simple cases where where you have only two elements and you think, well, hey, I know the currents. Still, every node will have a certain voltage associated with it, at least relative to other places in the circuit. And that's why it's useful to think about, like, well, what happens at one node depending on what I do at another node, and other such things. So moving on, if you look at E, C, and A, these three elements are all connected by ideal conductors, and I can just circle this intersection of these three wires right here and say that's a node. And this one is more interesting to talk about because three elements connect here, and this might actually be a case in a circuit analysis problem where you would apply Kirchhoff's current law and analyze the currents entering and leaving this node. Also, if you look down at E, F, and G, these three elements are all connected in this spot right here. So that's just like ECA, where you have three elements coming together. Now, there is one more node I'm going to talk about, and that's the case of 4 elements coming together here. And it's a little bit tricky. Well, so really, C, F, A, and B, these elements are all connected and they form a single node. And you might be tempted to say, oh look, C and F make a node here and A and B make a node here. But really, no, all 4 make a single node because they're all connected together by this same patch or intersection of ideal conductors. So this whole area that I'm circling here is really just a node. This is a short circuit between all these elements, and therefore this entire network of wires that connects these 4 elements would have the same voltage. So each terminal of these elements that's connected by these ideal conductors, there would be the same voltage on each terminal for each element. So this whole thing is one node. They're all shorted together. They're all sharing the same ideal conductor. And one thing you'll notice is that I drew these voltage polarities across these elements, and that's sort of unneeded information in this case. There's really no reason that I had to draw that to answer the question that I asked here. And I sort of drew them just arbitrarily, just to give you a feel for something that you might see in a circuit. It really doesn't matter, because I've drawn general circuit elements here. We don't know what these are. They could be passive resistors consuming power. There could be sources in here generating power. And the polarities can do all kinds of things. So, and it's also, you should be careful when you think about this, because what I've drawn are voltages across elements. So that VB is this voltage across element B, and VA is this voltage across element A. And so it doesn't matter, I've got this, what does it mean that I have this minus symbol here and this plus symbol here, and then, here I have 2 pluses near each other. Those don't need to conflict or interact in any way. There's no meaning in that. What I'm drawing are voltages across these elements. So the pluses and minuses from different elements, that's not an issue, or those aren't interacting in any way. I'm just talking about, like, this is the voltage across this element. So that's that problem. Again, I didn't have to draw any of these voltages to ask this question, but I just want to start getting you familiar with circuits. So real quick, let's count this up. We have 1, 2, 3, 4. It looks like 5 nodes in this circuit. Okay, now that was a nice quick example. I think I'm going to do one more in this video. So let me go ahead and draw up another example circuit, and we'll actually do, I think, some KCL. Okay, here we go. One last example in this video. I've drawn another circuit with 5 elements here. We have element A, element B, C, D, and E. What I've done are label a bunch of currents. So I have the current through each element. We have IA, IB, IC, ID, IE, and I have another current here, which I'm saying we know. So we know that IB is 2 amps. We know there's 3 amps flowing here, and we know that IE is 2 amps. And the question I'm going to ask is, what are IA, IC, and ID? And this is really easy to figure out. We're going to use a simple application of Kirchhoff's current law, KCL, to identify these currents. So the first thing I would do is look at, let's say, this node right here. We learned how to identify a node like this based on looking at the last circuit. And another interesting thing here is we're going to use KCL, and we're actually, notice I didn't label any voltages anywhere. We don't know what these elements are or what their voltages are, but it still makes sense to apply Kirchhoff's current law. It's still true. So that's another thing to consider when you do circuit analysis. What information in this case that you don't need, and again, what information in this case do you not really need, or what information is important. So now let's do a quick KCL here. So we're going to just say that because KCL says that the sum of the currents entering a node is 0, and the sum of currents leaving a node is 0, another way to look at that is that the sum of currents, well, all the current entering the node must then equal any current leaving the node. That's just another way of rearranging the algebra. So I can easily write out here IB plus IC equals 3 amps. So we have IB and IC coming in and 3 amps coming out. So this statement is true. And we see that IB is 2 amps, so 2 plus IC equals 3. Well then, it's pretty obvious. IC equals 1 amp. Okay, great. We're 1/3 of the way there. Now, what node can we look at next? How about this one? And notice I kind of sloppily drew this element such that I'm not connecting exactly to the corner on this side, but it doesn't matter. This little intersection here, this whole thing is the node. So we have another easy case of we have this much current coming in and we know there's a current leaving, so those two things must be equal to each other. So we have that 3 amps plus IE equals ID. And we do have another piece of knowledge here that IE is 2 amps. So if IE is 2, then we know that ID, therefore, is 5 amps. Okay, fantastic. Now let's solve for our last piece of unknown here, which is IA. And in this case, I'm not even going to apply a KCL because again, these two elements, A and B, are in series, and all you have to do here is identify the interaction of the current with the reference polarity that we've assigned here. So A and B must have the same current, and we know that B's current is 2 amps, and we know that it's positive in this direction, flowing to the right here. Well, IA, it must be 2 amps, and it must actually be flowing in the same direction up towards IB, because we already know this. So what we say then is that IA equals negative 2 amps. And that negative just comes from the fact that the arrow drawn on this circuit is in the wrong direction. So it is 2 amps. It's just a question of what direction. If this arrow for IA were pointing upwards, matching the polarity of IB, then I would write positive 2. It's just because of this reference polarity that I have a negative 2. And this is what I've talked about in past videos, where you don't actually need to know, say if you don't have enough info about a circuit, you don't actually need to know which polarity a voltage has, or which reference direction, or which direction current actually flows, because it will reveal itself later in the problem. Because the arrow is drawn this way, it's revealed once we find the solution that this is actually wrong, the current flows the other way. And that's one of the beautiful things about circuit analysis, that it is very general, and there's a lot of arbitrary choices we make, and that there isn't too much fundamental going on. I mean, the fundamental interactions at play are really limited, and there's a lot of room for generality. And one more thing we can do, and that you should do, especially when you're starting out in circuits, is find ways to check your work. And if you paid attention, you'll notice that there's actually one node that we didn't even use in this problem, but we can use KCL again just to verify the validity of our result. So there's a node right here where A, C, D, and E all interact. And let's perform a KCL there, and that should work out. And so if our calculations for I, A, C, and D were correct, well, if we get a correct answer here, it will better assure us that we made the right choices for I, A, C, and D. So if we perform a KCL here and it matches and we get the right answer, that's not proof that we calculated the correct currents for A, C, and D, but it does support our case a lot. So that's something you should do to check your work. Now, if you tried to do a KCL here and you didn't get the right answer, then you would for sure know that you're wrong. so that is something you can do to catch mistakes. So let's say that all the currents entering equal all the currents leaving. So in this case, we know that we have IA, well, we can say that because -2 is entering, we can just say that +2 leaves. So we have 2 leaving plus IC leaves, and we know IC is 1. That's 1 amp. And then IE leaves, and that's 2, so that's 2 amps. And then it must equal the current entering, which is ID, and that's 5 amps. And you can see that what we've done is check our work with this KCL, and so this actually agrees. we have a total of 5 amps leaving and a total of 5 amps entering. So that actually works out, and that gives us just a little bit more confidence that we've made the right calculations up to this point. Okay, so that was a good 2 examples. I think the video is getting a bit long, so I'm going to cut it here. I think the next video I'm going to continue to do some examples, and I'll step through and get a little bit more complicated and involved in each case. I hope this was helpful. Let me know if there's anything I can do to improve this in the future. And I hope you enjoyed, and have a great day.